Alright guys, in this section we're going to be discussing trigonometric form of a complex number. And in your algebra course, you have learned to add, subtract, multiply, and divide complex numbers algebraically. But to work effectively with powers and roots of complex numbers is going to be helpful to write complex numbers in trigonometric forms, as we'll see in this section. Okay, let's first consider the non-zero complex number a plus bi, just like I have it plotted here at the right. Now, letting this theta be the angle from the positive real axis, and we're going to measure it counterclockwise to the line segment connecting the origin and the point A, B, we can write the following. Given our complex number z equal to a plus bi, we have that the r here representing the hypotenuse of this right triangle is really our modulus, right? Which we also call the absolute value of z, or the complex number. Now this angle here that we're talking about, formed with the real axis, positive real axis, is going to be called the argument of z. Now if we use our right triangle trigonometry that we've been studying so far, we can set up a cosine of theta to be equal to a over r. Right? Remember, a here is one of the coordinates of our point here, and in the same way, sine of theta is going to be equal to b over r. Right? You can also look at the right triangle and come up with those ratios as well. Now, solving for a and b, we're going to get that a is equal to r cosine of theta, b is equal to r sine of theta. Now, remember here, this is something we've done before in other topics, but now we're applying them into the context of complex numbers. R here for us is the modulus, theta is going to be called the argument. So we can replace our z equal to a plus bi with an expression in terms of the modulus and the argument. So that will be equal to r cosine of theta plus r sine theta I. And notice how they both have r in common, so we can factor that out. So now we can write a complex number, z, as its modulus times the cosine of its argument plus I sine of its argument. So this is what we call the trigonometric form of a complex number, right? And it's called that way because for obvious reasons, you see cosine and sine in there, and we use an angle that we call the argument. Now remember the modulus, let's just recall the modulus is equal to the square root of a squared plus b squared from the previous section. And this argument, we can find it from the equation tangent of theta, or tangent of the argument, is going to be equal to b over a. So that we can find theta with our tangent if needed. Okay, so let's look at an example here and see how this works. Write the complex number z equals 6 minus 6i in trigonometric form. So here we have a complex number in standard form. We're going to write it with this new form here, the trigonometric form. Now we need two things. To be able to write a complex number in trigonometric form, we're going to need the modulus and the argument, right? Once we have those two things, we have everything we need. So let's find the modulus first. And we know how to find that. It's the square root of a squared plus b squared. And a is 6, b is negative 6. So we do the square root of 6 squared plus negative 6, all of it squared. That's equal to the square root of 72, which is equal to 6 square root of 2. Once we find the modulus, we are ready to find the argument. And tangent of the argument is equal to b over a, and that's negative 6 over 6, which is just negative 1. This negative 1 is actually a value from the unit circle, so we can come up with our theta here. When is tangent equal to negative 1? And if you think about the angles from 0 to 2 pi, we're going to get the tangent is negative on the second and fourth quadrant. And it's equal to negative 1, specifically at 3 pi over 4 and at 7 pi over 4. Okay, but which one is the argument out of those two? Only one angle could be the argument. And turns out that it's 7 pi over 4, because if you look at the standard form of the complex number, 6 minus 6i, if you were to graph this number in the complex plane, as we did on the previous section, you'll see that the number, the z, 6 minus 6i, is actually on the fourth quadrant, because a is 6, b is negative 6, so that's in the fourth quadrant. So then the argument has to be 7 pi over 4 because that's the one on the fourth quadrant and not 3 pi over 4. So you got to be very careful there. Now, it doesn't matter which coterminal angle you choose. You could have picked negative pi over 4 if you had done the arctangent of -1. That would have given you negative pi over 4. You're going to have an infinite amount of angles that work for the argument. You just got to make sure that you pick the right quadrant, right? You don't want to get an argument that is not in the right quadrant where the complex number is. All right, so once we have the modulus and the argument, then we can set it up from our form here. The z is going to be equal to the modulus, which is 6 square root of 2, times cosine of the argument, 7 pi over 4, plus I sine 7 pi over 4. And there we have it. We just leave it like that in terms of sine, cosine of the argument with the modulus there. Okay, so here we have another example, and this is the other way around. If you're given a complex number already in the trigonometric form, and you're asked to find the standard form, then you're just going to evaluate what you have there. So notice here from what we're given, z equal to 8 times cosine of 2 pi over 3 plus I sine of 2 pi over 3. To get into the standard form, just evaluate that cosine and that sine. And 2 pi over 3 is from the unit circle, so you should be able to do that without a calculator. Cosine of 2 pi over 3 is -1/2 plus I sine of 2 pi over 3 is square root 3 over 2. Okay, finally we're going to distribute that 8 and we get the z is equal to -4 plus 4i square root of 3. And there we have our complex number in standard form. Now if you were to graph this and the complex plane, you see that we end up in the second quadrant. And that makes sense because look at the argument. It's 2 pi over 3 and 2 pi over 3 is in the second quadrant, so it agrees with our answer here. All right, so next we're going to see how to compute the product and the quotient of two complex numbers. Let's start with two complex numbers, two generic arbitrary complex numbers here, z1 and z2, and I'm have them here already in trigonometric form. And this is going to be the idea, how to compute the product or the quotient of two complex numbers with their trigonometric form. So let me work through a product of two complex numbers and kind of in this way derive the formula that we're going to have. And for the quotient, it's going to work similarly, but for the sake of time, I'll let you do that on your own. We'll just state the formula for the quotient. But it's going to be very similar than the product. And we're going to have to recall some of the identities that we've discussed previously to be able to condense our results here. So if we multiply a complex number z1 with another complex number z2, notice how I'm literally going to distribute this out. We have the trigonometric form of each one. R1 and R2 are just the modulus of z1, z2 respectively. So I can put those two together, right? They're just real numbers. Now, the other two expressions in the parentheses, I'm going to go ahead and FOIL that or distribute. Let's see what we get. So I'm literally just multiplying, distributing every term, right, on those expressions. So I'm going to get cosine of theta 1 times cosine of theta 2 plus I sine of theta 2 times cosine of theta 1 plus I sine of theta 1 cosine of theta 2 plus I squared. Right, because I times I squared, sine of theta 1 times sine of theta 2. So I accommodate it in a way that it's nice and readable. Since the order of the factors doesn't alter the result here, you can write it whichever way looks better. Now, notice here, I'm going to group, I end up with 4 terms here, and I'm going to group the two that don't have an I, and then the other two that have an I in them, I'm going to group those together. Now notice here this last term has an I squared, but if you recall, I squared is -1, which is going to make that plus negative. So I'm going to put that one, the first one and the last one together, since that I squared went away. I'm replacing it with a -1. Okay, so I end up with cosine theta 1 times cosine of theta 2 minus, right? So I'm bringing that last term here together with this first term, sine of theta 1 times sine of theta 2. Now, in the other two terms, since they have I in common, I'm going to go ahead and factor that I out, and I get this. Yeah, I switched the order here, but that doesn't matter since we're adding, and it's going to be the same thing. Now, what I have in parentheses here should ring a bell from your set of identities. This first parenthesis is actually the cosine of a sum, and this other parenthesis is the sine of a sum of two angles, right? So I'm going to condense that using my sum and difference identities, and I get cosine of theta 1 plus theta 2 plus I sine of theta 1 plus theta 2. Okay, so here we have it. That would be our formula for the product of two complex numbers, and this is already in trigonometric form. Now for the quotient, it's going to work similarly. Just for the sake of time, I'm going to skip all that work. And we're going to get that instead of adding the arguments, we'll actually subtract for the quotient. Everything else is the same. Now, of course, we want z2 to not be equal to 0 so that the quotient is actually defined. Now, remember, we still have the modulus multiplying on the product, and for the quotient, we have the modulus dividing, R1 divided by R2. So let's look at an example here to see how this formulas work. Find the product z1 times z2, and they give us a z1 equal to 2 times cosine of 5 pi over 6 plus I sine 5 pi over 6. And z2 is equal to 5 cosine 7 pi over 6 plus I sine of 7 pi over 6. Okay, using the formula here, I'm going to get the product of the two modules, 2 times 5, and then times cosine of the sum of the two arguments. The first argument is 5 pi over 6, the second one is 7 pi over 6, and the same thing for sine. We have plus I sine of the same sum. All right, once we have that, we can start simplifying some things. 2 times 5 is 10, and we get that all that is times cosine of the sum of the two angles here. So 5 pi over 6 plus 7 pi over 6, that's 12 pi over 6, which is 2 pi. Okay, so that's nice. Plus I sine of also 2 pi. And there we have it. That's the product of z1 times z2. Now, if you wanted to write this in standard form, we'll get that 10, we just evaluate, right? Cosine of 2 pi and sine of 2 pi. Well, cosine of 2 pi is just 1, sine of 2 pi is 0. So that whole thing goes away, the imaginary part, and I'll just get 10 times 1, which is equal to 10. So this whole product was just equal to 10, which is a real number. Okay, so now let's look at an example with a quotient. Find the quotient z1 over z2, and we have a z1 equal to cosine of 40 degrees plus I sine of 40 degrees, and z2 is cosine of 10 degrees plus I sine of 10 degrees. So I'm just using degrees instead of radians here just to mix it up a little bit, but it's the same idea. z1 over z2 is going to be the quotient of the modulus, and in this case for both complex numbers the modulus is 1, right? So it'd be 1 over 1, all that times cosine of the difference of the arguments. 40 degrees minus 10 degrees minus I sine of 40 degrees minus 10 degrees. So again, for a quotient is minus instead of plus, right? So that's going to give us a nice angle here from the unit circle. So we got cosine of 30 degrees minus I sine of 30 degrees. Now we can do those quickly from the unit circle. We get that cosine of 30 degrees is square root of 3 over 2 minus sine of 30 degrees is 1/2, and we have the I. And there we have our complex number in standard form. All right, now that we know how to multiply and how to divide complex numbers, we can start talking about powers of complex numbers, which will eventually lead us to finding the roots of complex numbers as well. All right, so let's start by just defining our complex number here, z equal to r times cosine of theta plus I sine of theta, so just a regular trigonometric form of a complex number. And let's start with the smallest power here. Z squared would be equal to z times z. We already know how to find the product of two complex numbers. In this case, we're multiplying a complex number with itself. So if we apply the formula that we just finished doing, this would be the modulus times the modulus. In this case, it's the same thing. R times cosine of the sum of the two arguments, but since we're multiplying the same complex number, or a complex number by itself, then we just add theta plus theta, and we're gonna get r squared times cosine of d theta plus I sine of d theta. If we keep going this way and just do the next power, z cubed, we get that z cubed is equal to z squared times z, and we just found what z squared is on the previous step here. So if we multiply that times z again, we're going to get r squared times r, and then we're going to add the arguments, right? Cosine and sine, right? Hopefully you start seeing a pattern here, right? We're going to get r cubed times cosine of, we have 3 theta now, plus I sine of 3 theta. Okay, notice how the argument has a multiple here that matches the power of the complex number. If we continue in the same fashion here, we're going to get this nice theorem here. It's called the Morse theorem, and that says that a complex number raised to some power n is equal to the modulus to that power of n times cosine of n theta plus I sine of n theta. In other words, you're multiplying your argument times n in your trigonometric form. So let's look at an example to see how this works. We have find -1 minus I raised to the 4th power. So this -1 minus I is our complex number. And the first thing we got to do is we got to write this complex number in trigonometric form. To be able to use the theorem here, we got to have it in trigonometric form. And to do that, we have to first find the modulus and the argument. We've already done some practice with this before. So let's go ahead and find the modulus of -1 minus I. And that's just r equal to square root of -1 squared plus -1 squared. So that's equal to square root of 2. And then also the argument comes from tangent of theta equal to -1 over -1, which is 1. Now you gotta be careful here. Make sure that you get the right argument, because if you do arctangent of 1, that's gonna give you pi fourths. That's first quadrant, but RZ, if you graph it, is on the 3rd quadrant. So then the theta, or the argument, has to be 5 pi over 4. And since tangent of 5 pi over 4 is also equal to 1, that's the one that works. Okay, theta is in the 3rd quadrant, just like your complex number z is. All right, so having the modulus and the argument, now we're ready to raise this number to the 4th power. I'm going to write the trigonometric form of -1 minus I in here, and we're going to raise this to the 4th power. Now, using our theorem here above, we're going to get that z to the 4th power is going to be equal to the modulus to that 4th power. The modulus is square root of 2. We're going to raise that to the 4th power, and then that's going to be multiplying cosine of the argument theta is going to be multiplied by 4, since n is 4, plus I sine of the same thing, 4 times the argument. The argument for us is 5 pi over 4. So we're multiplying 4 times 5 pi over 4, and we get this. Okay, 4 times 5 pi over 4, the 4's cancel out, and we get a nice 5 pi here as a new argument. And square root of 2, the modulus to the 4th power, square root of 2 to the 4th power is just a nice 4. All that multiplied by cosine of 5 pi plus I sine of 5 pi. Now 5 pi is coterminal with pi, so cosine of 5 pi is the same thing as cosine of pi. Cosine of pi is -1. Sine of pi is 0, which eliminates that imaginary part. So we end up with 4 times -1 is equal to -4. So notice how that power, -1 minus I to the 4th power, is just -4th, which is a real number. Now imagine if you had to do this algebraically. You have to FOIL this number or distribute it, -1 minus I times -1 minus I. Right? It would be very hectic, very time consuming, very inefficient. So this theorem here, the Morse theorem, helps us find this power in a more efficient way. Okay, now we're ready to define the nth root complex number. So if we have this complex number u equal to a plus bi be a nth root of a complex number z, this is going to happen with u to the nth power give you is equal to that z number. Okay, so think about as if you were to take the nth root of the z number, you get u back, because if you do that on both sides of the equation, the n cancel out with the nth root and you get just u. Now we're going to have this nice formula to find the nth roots of a complex number, and you're going to have exactly n roots. For any given power, you're going to have exactly that amount of roots. Okay, after that, we're going to have we're going to start repeating. So we get this formula here that for a positive integer n, the complex number z equal to r times cosine theta plus I sine theta has exactly n distinct nth roots given by, and we're going to call them z sub k, right? Where k goes from 0 to n minus 1. Since we're counting to 0, we're going to have exactly n roots. And this comes from the famous theorem in algebra, the fundamental theorem of algebra, that says that in the complex number system, you have any polynomial has exactly nth roots when n is the degree of the polynomial, okay? So let's look at an example and see how this works. In this example, we want to find all fourth roots of 1, just number 1. 1 is just a real number, but it's also part of the complex number system, right? Because remember, complex numbers include reals and imaginary. Now, the first thing you want to do is want to write 1 in its trigonometric form, and 1 is going to be equal to 1, that's this modulus, and the argument is 0. Because if you picture 1 in the complex plane, it's right on the real axis there, the positive real axis. So we have 1 times cosine of 0 plus I sine of 0, right? So notice how the modulus is 1, as we said, and the argument is 0. Okay, with that, we can substitute this into our formula and figure out all four roots. Okay, so we're going to start with k equal to 0. We have z sub 0, our first root, is going to be equal to, again, n for us is 4, guys, because we're finding all fourth roots of 1. So it's equal to fourth root of 1 times cosine of the argument 0 plus 2 pi times k. In this case, our k is 0, all over 4 plus I sine of the same thing, 0 plus 2 pi times 0 all over 4. Okay, so we're just gonna go ahead and set up all the roots here, and then we'll calculate them. For the next root, z sub 1, have the fourth root of 1 times cosine of 0 plus 2 pi times 1, which is our k, all over 4, plus I sine of the same thing, 0 plus 2 pi times 1 over 4. All right, so all the roots are the same, are following the same formula here. The only thing that's changing is the k. We're moving up from 0 all the way to, since n for us is 4, we're going to go all the way to n minus 1, which is 3 for us. So we'll have z sub 0, z sub 1, z sub 2, z sub 3, which is a total of four roots. All right, so z sub 2, we have same fourth root of 1 times cosine of 0 plus 2 pi times 2 over 4 plus I sine of 0 plus 2 pi times 2 over 4. Okay, and then finally our fourth root would be z sub 3, which is equal to fourth root of 1 times cosine of 0 plus 2 pi times 3 over 4 plus I sine of 0 plus 2 pi times 3 over 4. And there we have our four roots. Let's go ahead and simplify this a little bit. And the fourth root of 1 is just 1 for all of these. And let's see, on the first one, we have cosine of 0 plus 2 pi times 0, that's just 0. So everything is 0 on top, divided by 4, still 0. So we have cosine of 0 plus I sine of 0. Okay, in the next one we have 1 times cosine of 2 pi over 4, which is just pi over 2, plus I sine of pi over 2. The third one we have cosine of 4 pi over 4, which is just pi, plus I sine of pi. And then last one we have cosine of 6 pi over 4, which is same thing as 3 pi over 2, plus I sine of 3 pi over 2. All right, so here we have all our four roots in trigonometric form. If you wanted to see how these roots look like in standard form, we'll just evaluate the cosines and the sines here. And luckily for us, the angles are really nice. They're from the unit circle, so we should be able to figure those out right away. We have cosine of 0 is just 1, sine of 0 is just 0. So when we do that on the first one, we get that that's equal to 1. On the second one, cosine of pi halves is 0, sine of pi halves is 1, so I get 1 times I, which is just I. And in the same way, the third one we get negative 1, and the fourth one we get negative I. So there we have all our four roots of 1. What does that actually mean? Well, we just calculated all the four complex numbers, then when you raise them to the fourth power, it gives you 1. So that's the fourth roots of 1. That's what that means. One of the interesting things about this formula is that what we find here are not only numbers that when you raise into the fourth power gives you 1, but also they're the only ones in the whole complex number system that when you raise into the fourth power it gives you number 1. And you can verify that. 1 to the fourth power is 1, I to the fourth power is 1, negative 1 to the fourth power is 1, negative I to the fourth power and 1. And something else that you notice graphically, if you were to put them here on a circle with radius 1, because the modulus was 1, they all happen to be equidistant from each other, right? Notice how in this case we have 1 root on each axis here. In the real axis, positive imaginary axis, the negative real axis, and the negative imaginary axis. But the point is that you see them are equidistant from each other. Let's look at one more example where we're asked to find in this case, all 3 cube roots of z equals to negative 6 plus 6i. The first thing you want to do, if you're given the number in standard form, you want to write z in trigonometric form. So that's the first thing we're going to do. Now, to be able to do that, we need to find the modulus in the argument. So the modulus would be the square root of negative 6 squared plus 6 squared, which is the square root of 72. Simplified is 6 square root of 2. The argument comes from the equation tangent of theta equals to b over a, which is 6 over negative 6, which is equal to negative 1. Now from here, when is tangent equal to negative 1? Tangent is negative in the second and fourth quadrant. But look at where z is. If you were to graph z, negative 6 plus 6i is actually on the second quadrant. So then theta has to be 3 pi over 4. That's our argument here. Okay, so once we have the argument and the modulus, we're going to write z in trigonometric form. So that's going to be equal to 6 square root of 2 times cosine of 3 pi over 4 plus I sine of 3 pi over 4. All right, so applying our formula here, we're going to start with our first root, z sub 0, and we start by taking the cube root of the modulus. So it's going to be cube root of 6 square root of 2. You could also do the cube root of square root of 72. Whichever way, we're going to have to put this in the calculator if we want to approximate something once we're done with the trigonometric form. If we want to get them into the standard form, we're going to have to, put these values in the calculator to get an approximation. So the first root is the cube root of 6 square root of 2 times cosine of, and we're just going to start adding, right, our argument plus 2 pi times k is 0 here, so 2 pi times 0 over 3 plus I sine of the same thing. Remember, n for us is 3 since we're asked to find the 3 cube roots of this complex number. Okay, in the same fashion, we're going to do the other two, z1 and z2. And if you were to keep going here, guys, if you were to do z3, z4, and so forth, you're going to start repeating the other. So that's why the formula is given to you that way, because these are the distinct roots. And if you kept iterating that k, and in this case, kept going z3, z4, you're going to see that z3 is actually the same thing as z0, z4 is the same thing as z, and it starts repeating those first 3. Notice how I did approximate that cube root of 6 square root of 2, and that was 2.0396, and we get that. Now, you could find those cosines and sines. They're not from the inner circle, not all of them, so I'm just leaving them in trigonometric form. But if you wanted to write them in standard form, you would just evaluate those and distribute that modulus, the 2.0396, and get a standard form. But again, notice how if we were to plot these points in our complex plane, you see them equidistant from each other on the circle. And this circle is of radius, whatever the modulus is. So in this case, the radius would be 2.0396, right? So that's the radius of the circle. But the point is that those roots fall right on that circle, not only on that circle, but also they're equidistant from the next root. And if you raise all these roots to the third power, you're going to get our original complex number, negative 6 plus 6i. There we have it.